Okay, so these random integration with different parts, right? We have an integral, and we're trying to take the antiderivative of it. Right? That's the whole entire point, where there's about 9 or 10 different ways that we've been able to do this, right? Just direct antiderivatives, right? If it works like that, there's natural log antiderivatives. Today's basically are going to all be inverse trig antiderivatives. So let's write down what those are real quick. So these are the most commonly used antiderivatives for arctrigs, right? So arcsine or inverse sine and arctan are the ones used most often. So we're going to want to try and make our denominator look like one of these things. Okay, that's what we want it to look like. We want to have a u squared. Your variable is going to be in the u part, and the a is going to be some number, right? This could be x plus 1. It could be just x. It could be 2x. It could be e to the x, right? So whatever that function happens to be, u is going to be a function. Sometimes like g of x or something. We'll just leave it as a u. So looking at example 2, right, the one here where it says completing the square, we want to make the bottom into something squared plus something else squared. Right? If we could do that, then we could use that arctan as the inverse or the antiderivative. Okay, so that's our whole goal, is we're trying to create something that is easily antiderivable or easily integratable, since those words are synonymous. Okay, so we do this by a process called completing the square. Right, so we want to use these two terms in order to make it into a perfect quadratic. Because a perfect quadratic factors to something squared, right? Whatever that happens to be. That's what we're going to do, is we're going to make that into a perfect quadratic that factors into that term. So you might have forgotten how you complete the square, or you're all geniuses and you remember everything, which is probably the case. X squared minus 4x plus some square. Right, we're going to call that the square. But in order to stay balanced, we also have to subtract that square. Okay, yes, I should have made a much longer vinculum there. So there we are. This is going to be your perfectly factorable quadratic. Right, and then the rest of this is going to be your hopefully plus a squared. Maybe. Right, well, we can always write it as something plus a squared. We can do that just fine. So what number goes in the box, right? That's the question. What is this perfect square that we're talking about? Well, it always is dependent upon this number. And what we do is we take half of that number and we square it, right? That's this part right here. Half of b squared. So half of negative 4 is negative 2, and negative 2 squared is 4. So we're going to put a plus 4 and a minus 4, because what is 4 minus 4? 0, right? We're adding 0 to this equation, which doesn't change. Adding 0 to my bank account doesn't make me any richer, unfortunately. But it doesn't. But what it does do is makes this into a perfectly factorable quadratic. So what does that factor to now? X minus 2. That factors to x minus 2. Because what numbers multiply to give you positive 4 and add to give negative 4? Negative 2 and negative 2. Now what is our other term? Negative 4 plus 7 is plus 3, right? Plus 3. Well, that's not a perfect square, is it? No, it's not. But I'm going to change it so that it is a perfect square. And you can do this too, anytime you want. So we have dx over x minus 2 squared plus the square root of 3 squared. Haha. What is the square root of 3 squared? Well, it's just 3, of course. So we can do that with any number. If this number is not a perfect root, then just take its square root. And then your a value is going to be root 3, and your u is x minus 2. Okay, so when we do this substitution right into our arctan formula, these are the numbers that we're going to use. So this is an arctan antiderivative, right? It's the derivative over something squared plus something else squared. Okay, so what goes in the box? On top goes our u, so x minus 2, and on the bottom goes the a value. And then, of course, there's this gluttonous plus c hanging out there just for fun. Okay, let's look at this one. Here we have a nice square root, right? 1 over the square root. So this is probably thinking this is going to be some type of an arcsine antiderivative. Okay. Only the arcsine has this format where it's 1 over the square root of a squared minus u squared. Okay. So this looks like it could be manipulated into making it an a squared minus u squared type of deal. Okay, that's right. That's your thought process. Is we want it to be something that's easily anti-derivable, and right now this is not easily anti-derivable. So let's just mess with the denominator here for a second, and I'll put it back in. So 3x minus x squared. We're going to add. We're going to complete the square. So we add a box and we minus a box. All right, we have to add a box and minus a box. So what goes in the box? Well, it's always half of this term squared. So half of 3 is 3 halves, squared is 9 fourths. So we're going to add 9 fourths and subtract 9 fourths, right? Because plus 9 fourths and minus 9 fourths, well, that's 0. So I'm not really changing my equation at all, am I? And sort of am. So what do these 3 terms factor to become? They factor to become 3 halves minus x quantity squared. It's always the derivative, the square root of your numerical term. Okay, so the square root of 9 fourths is once again 3 halves. It's this answer right here that we squared a moment ago. So 3 halves minus x quantity squared. And we also have a minus 9 fourths plus that. Okay, so let's write this kind of how we want it to be written. Right? Well, how do we want it? We want it to be the integral of 1 over the square root of, let's write this in its squared form. So that would be 3 halves squared plus, well, I guess the negative of 3 halves squared plus 3 halves minus x squared, which isn't exactly our arcsine, is it? But let's make it, because we're going to manipulate this thing until it works. What if I pull the negative out here? Is that okay? What if that happens? That means I now have a positive 3 halves squared minus 3 halves minus x squared. Right? So there are devious little algebra things that we can do in order to make our equation exactly how we need it to be. So this is the square root of the negative of a squared minus u squared, which just means our integral is going to be negative, right? The answer will be negative in the end rather than the positive. So negative arc sine rather than positive arc sine. So let's see, negative arc sine. So that's an ugly looking S. Oh, geez. Okay, arc sine or sine inverse of your u term, which is 3/2 minus x, over your a term, which was 3/2, and plus c. Okay, so yes, they can be definitely algebraically messy, but what we're trying to do is do some manipulation so that our answers look like something that we can take an easy inverse trig antiderivative of. Okay, let's see some other comparisons here as we try to fit some integration rules. So these look pretty similar. 4 over x squared plus 9, 4x over x squared plus 9, 4x squared over x squared plus 9. Right? So these are very similar, but I bet you the approaches, right, the solving part is going to be different. So this one, I'm pretty sure this is going to be an arc inverse trig derivative. Right? We can pull the 4 on the outside. That's one of our rules that we can do. And this is x squared plus 3 squared dx. Right? That looks like it's going to be an inverse, sort of arctan derivative. So this one does, in fact, integrate to being an arctan, right? 4, because there's a 4 out front. So 4 arctans of, whoop, not that one, of x over 3. Right, your a value is 3 and your u value is x. So 4 arctans or inverse tans of x over 3 plus c. Okay, B, let's see. B doesn't really look like it's going to be an arc trig inverse, right? Because we have a 4x on the top and an x squared. This might be a good u substitution problem, right? This might be a good u sub problem. So let's check that out and see if that works. What if we let u be equal to x squared plus 9? Then du is 2x dx, right? So, I mean, like, the problem with math is it's an awful lot like medicine. It's a practice, right? And if one thing doesn't work, then you got to try something else. It's almost always figure outable. Okay, almost always, right? Sometimes we're like, crap, I'm just giving up. And we move on, and that's okay. You're a good person still, for the most part. So 4x over, well, this is u now, right? I let x squared plus 9 be u. And then dx I replace with du over 2x. Okay, so what simplifies here? The x and the x, right? Divide out, which is excellent. If they did not divide each other out, then this would be a bad way to try and solve this. And 4 divided by 2 is 2. So I'm going to pull the constant to the front of my integral, like we do with all constants. And I get 1 over u du. Okay, so then what is the antiderivative of 1 over u? That's the natural log antiderivative. And then we're going to put our u back in there, which was x squared plus 9. Okay, which, by the way, is always positive, so we don't really have to have that absolute value around there. But if this were a multiple choice test, that's what you'd see. You'd see the absolute value. Okay, so we did this one with an Arctrig, right? We noticed that it was in an Arctrig, an inverse tan kind of setup. Okay, this next one was a good U substitution problem. We looked at that one, right? And that worked out nice because the x's cancel out. Remember, if the x's don't cancel, then U sub is not a good way to go, right? Part C, we tried integration by parts and got bogged down and did some other things. So I don't know. We got more questions about that one. But then down here, right, a couple more comparisons. We noticed that this one was an inverse secant. Okay, we looked it up, and this is the antiderivative of the secant equation. This one was once again a U substitution. We let U be x squared minus 1, and we got a nice square root antiderivative. And then our last one, we made this into some manipulation and manipulated it into being a sine. Hopefully that was correct to do that one right there. Okay, so if one doesn't work, I'm sorry, but you got to erase and try another one. So trial by error, I guess. Okay, that's all. Have a great day. Goodbye.